Hello everyone, can you am I live now? Good morning. Uh Live now? Not sure. Yes. Yeah. Hey, hey. So get started. So welcome to 125 again. Let's have the Kahoot game first, quiz game. There are 46 players for this quiz right now. I'm going to flash the questions. So I'll start in 11:06 on my time here before I start the. I want you to indicate your section so that you'll have some bragging rights for your lab section. There will be a podium, top scorer for this particular type of. So somehow the purpose this will not be graded, but the purpose of this is for you somehow to test whether if you study the material, then somehow this will test you whether you understood the some of the things that you studied for this class. So one more minute before I start the game. Can you see the question? I hope you can see the question, the stream. Quite difficult to manage a lot of things here. We're doing a lecture like this, but we'll manage. I don't know if there is a lag in your setup, but everyone will be able to answer. Okay, so I'll start the game now. Ready? Okay. Correct answer for this question is the device driver. Next. So CD7L, Mr. Pua. I see V Pua got the highest. Okay, let's move on to the next question. Okay, so the correct answer is true. The device driver, the device controllers, and the CPU they can execute concurrently. The okay, CVV Pua again, 7L got the highest score. Let's move on to the next question. Is caused by an error or a user request? Okay, so the correct answer is a trap or an exception. But I only have a free license for Kahoot, so only one option. So correct answer is trap. Aaron, okay, got the score here. CD7L. Okay. Next. Don't worry, this is a try. So if you're very competitive, we'll address this later. This is a test run. So the correct answer for this question is you should save the registers because you have to be able to go back to the previous instruction that was interrupted by the interrupt. So it's the register. Next. So okay, CVV Pua CD7L got the score, the high score. Then for the last question, okay, so the correct answer is direct memory access, which means that you have a block of memory, a block of data from the device, a disk block, and it can be directly placed to the memory. Correct answer is DMA or direct memory access. Here are the top scorers. Third is so there we have the following people. Okay, so we have LGL Talib, CD8L first, and CVV Pua and MR Malonzo. So CD8L won for today's quiz. Okay, so thank you very much for participating. I don't know your experience if you have lag, if you experience lag in your machines, but don't worry, this is just for fun. So at least you get to review whether you're learning, whether you learned something in the independent study that you're having for this class. Okay, so I hope you enjoyed that quiz. I will try to improve this later, but for now, we have this, have them. Okay, congratulations to the winner. So for today, we're going to talk about two sections in our from our textbook. We're going to talk about computer system architecture. And then the second one is we're going to talk about operating system operations. So we finished section 1.1 and section 1.2. So we now move on. We now continue to the next lessons. So DMA is like this, part of the quiz. So you have the devices, and they can directly write to the memory without interrupting the CPU after the I/O. So today we're going to talk about computer system architecture, and this is all about the way the processors are organized. So we zoom in into the processor, the CPU, and then we look into how the CPU is organized. It's important to understand this because when you write an operating system, you need to somehow understand how the processors are interconnected because the architecture will have implications in the design of the operating system. So for example, if you're writing an operating system for an x86, a desktop computer, general purpose computer, then you need to understand how, for example, how many cores is it doing uh, symmetric multiprocessing, etc. Because you need to factor that the architecture in the design of your operating system. So it's essential that you understand this. So most systems actually use a single general purpose processor. During the early days when I was a student, we only have one processor. So let's say we have a 286 processor or 386 processor, Pentium processor, etc. And the general purpose processor, the purpose is to perform the typical computation. So execute the typical instructions. But most computers also have special purpose processors as well. During the early days, there was actually no separate processor for floating point operations. And as you know, from ComSci 130, floating point operations are quite complicated and expensive. So they are integrated into the general purpose processor. But in time, they also developed special purpose processor for performing floating point operations. So, but the general idea here is you have a single general purpose processor before. Now, nowadays, we now have what we call multiprocessors. Okay? And of course, why is this evolving? There are several reasons. The first one is the need, right? The growing need for faster computations. Computing nowadays is used in many aspects of life, and the computations being performed are usually complicated. So they need to improve that. Like for example, nowadays, when it comes to artificial intelligence, okay, during the early days, there is a limitation in the computation. So we were not able to develop algorithms to classify, let's say, to perform image classification, etc. So multiprocessors were developed, and also the technology also has evolved. Okay? So the fabrication of different components became cheaper. So it's natural that we can improve the computing capabilities by adding multiple processors. And these are sometimes called parallel systems or tightly coupled systems. There are three main advantages, of course, of multiprocessors. The first one is increased throughput. So naturally, if you have more processors, then you can achieve more output. So this will increase the throughput. And then also economies of scale. So if you manufacture, let's say, multiple processors, then the computations that it can do will be somehow complicated also, and it becomes cheaper actually to manufacture machines with multiple processors in the long run. And then of course we have increased reliability if you have multiple processor. If you are solving a problem, for example, and one processor actually goes down, then the other processor, if you have a multiprocessor system, can do the job even if the other processor failed. So it actually increased the reliability. And there are two types of multiprocessing. Okay? We have first one, the asymmetric multiprocessing, wherein each processor is assigned a specific task. Okay? And the other one is symmetric multiprocessing, wherein each processor performs all tasks. When you say asymmetric processing, let's say you have uh, two processors here. I think we have a figure later in this slide. So the idea for asymmetric multiprocessing is one processor acts like a master and the other processor acts like a slave, and they have different roles. But if you have symmetric multiprocessing, whatever one processor can do, the other processor can do also. So some kind of a peer relationship. So these are multiprocessor systems. So this is an example of a symmetric multiprocessing architecture. So in this setup, so the entire block is we have a multiprocessor system. We have processor 0 and we have processor 1. And processor 0 has its own CPU. Okay? And it has its own set of registers and a cache. And processor 0 and processor 1, they can do the same tasks. Okay? And that's what we mean by symmetric multiprocessing. There is no designated master or there is no designated slave. And they also, again, given the setup, they also access the shared bus to access the main memory. So this is basically how symmetric multiprocessing architecture happens. For example, most machines are actually SMPs. Let's say have a multiprocessor machine. So normally you get something like this SMP. So this is a multiprocessing machine, and this is the server where I run my VMs. And as you can see, I have this is actually a 32-core machine. You can see this in the figure. So it has a lot of idle processors. And Linux can support symmetric multiprocessing, and each of these programs or processes can execute on the different processors depending on the availability. As you can see, the things fluctuate because that means that there is a task being done by that particular processor. This is not actually a multiprocessor architecture, but usually this is referred to as a multi-core machine. Okay, so that's symmetric multiprocessing architecture. And most systems nowadays are not actually called multiprocessors, but rather multi-core. When you say multiprocessor, like in the previous in the setup, this one box here, okay, this box here is manufactured in a single chip, okay? And these are the components. But in a multi-core system, okay, you have the one big box that this represents the chip and is called the processor, and you have multiple cores in this machine. And of course, it has, for storage, we discussed in the previous video, the storage, we have the registers and we have caches. L1 cache, L1 cache, and L2 cache. So normally the L2 cache is a shared cache, okay, as shown here, and then you have the main memory. So this is an example of a dual core design. You can see this in your machine. So LSCPU will tell you the specific characteristic. For example, in this machine that I have here, it uses the x86-64 architecture. It can support 32-bit and 64-bit. And there are 32 CPUs in this machine. And can have 2 threads per core. And regarding the clock, okay, so we have the clock here, 0.2. Then the sizes of the caches. So you have L1 cache, L2 cache, and L3 cache. In the previous illustration, we only have 2 level L1 and L2 cache, but here we have 3 levels, and the L1 cache has 2 types, one for data and the other one for instruction, which is 32 kilobytes. So this is a typical architecture nowadays. So if the creator of operating systems need to factor in this architecture in designing the operating system. And luckily, Linux, for example, if you're a Linux user, is being developed, always being developed and improved. Then you get the result, the support for multi-core system like this. So this is a server type machine. Let me check the Slack if you have questions. Okay, so I'll try that later about the ultra low latency. Okay. Thank you for the suggestion. I'll go back to that later. My setting here is normal latency in my setup. Okay, so there's no specific question about the topic here. So we now move on to the next. So there are also what you call non-uniform memory access system. Unlike in the previous design, like the dual core system, this example, we have a shared bus to access the main memory. So this is called uniform access because you have to have a shared bus. But to improve, the problem with this is that if you have multiple processors, they will contend for access to the memory. For example, only one processor can access the main memory. So what NUMA machine does is to have each CPU to have its own memory. Okay, so they don't have a shared bus, but the CPU here can directly access its own memory here, and CPU 1 can directly access this main memory here. And the other CPUs are interconnected via some form of interconnect. And the problem with this is that what if CPU 0 would like to access data from memory 3? So that will be a problem because CPU 0 will have to communicate with CPU 3 to be able to obtain access to the data that is being stored in the memory 3. Okay, so that is the non-uniform memory access system. But these are specific. This is a special type of architecture, and sometimes in data centers they have this type of setup to really improve performance, because nowadays the demand for computing is very high and performance is a very important metric. Okay, so the next one, so we discussed about multiprocessor, multi-core. Okay, now the next one is called clustered systems. Clustered systems are like multiprocessor systems, but you have multiple systems working together. Okay, Unlike in the multiprocessor and multi-core, you have a single chip or just multiple chips. Here you have actual uh, system, one full system with including the peripheral devices, okay, like the network card, entire package, entire CPU that you buy, for example, your desktop, okay, and they also perform, they solve problems together. They work together to solve a particular problem, but uh, they are independent systems on their own. For example, my laptop can be considered as part of a node in a clustered system. It can contribute, for example, to computations that is being performed online. Right? And usually, this clustered system shared a storage area network. I think you will not be able to see this in a typical setup in your home setup, but for example, in bioinformatics systems, in research centers, for example, in DOST, they have this setup, clustered system, because the problems that they are solving there are complicated problems related to bioinformatics, simulations, and many other computations. So usually they have storage area networks, which is a type of network that connects all the storage because they have to process large amount of data. Okay? And clustered system also provide high availability, which is in relation to fault tolerance. So meaning the services that is being provided, there is no, somehow the downtime is very rare. Okay? So the system is always up. So that's what we mean by high availability in terms of when a failure happens in one system, the data will still be available. This is actually useful in cloud-based systems. For example, your document, when you open a document in Google Drive, for example, your data is not just stored in one server, such that when that server is down, you will not be able to access your data anymore. So normally, your data is spread across different storage devices so that when one storage is down, you will still get your data. So there's a form of replication that is being done here. And there are two types of clustering also in the same manner as multiprocessing. Asymmetric clustering is as one machine in a hot standby mode. So the same definition actually as the asymmetric multiprocessing. Okay, so you have one machine that has hot standby mode for the asymmetric. For symmetric clustering, it has multiple nodes running applications monitoring each other. The same manner the symmetric multiprocessing is described earlier. And if you're going to do research in distributed computing, then clustered system is a very good example of that. And some clusters are used for high performance computing, as I mentioned a while ago, bioinformatics, computations, volcanic and earthquake simulations. These things are quite complicated, or let's say chemical calculations. Right? So they are used in high performance computing. Normally, it uses some kind of a framework. For example, MPI. MPI, or the message passing interface. The idea here is, again, you have different systems, and then the MPI is some kind of a middleware that allows you to access or to distribute tasks in other among different computers. If you're going to take, I don't know, I think ComSci 180 is required in your curriculum. If you're going to take ComSci 180 next semester, you're going to learn about clustered systems, and specifically, you're going to study the message passing interface for cluster programming for the purpose of high performance computing. Okay? And the requirement is that the application must be written to use parallelization. Okay? So an example of this is in matrix computation. For example, matrix multiplication. So when you write a program to solve the matrix multiplication, to compute matrix multiplication, you need to write it nicely so that it fits the framework of the MPI. So it's not just the normal programming that you, let's say you have a nested for loop, 3-level nested for loop to find the product of two matrices. Not just like that. You have to do some reprogramming or reorganization of your code to be able to run that in a clustered system. And the main problem, the main issue with clustered system or any parallel system is, of course, simultaneous access to data and the importance of consistent data being stored. And to solve that, there is what they call a distributed lock manager. We'll discuss this when we talk about synchronization, but the idea here is you have a lock manager that grants access, who can do this, who can do that, so that not everyone will be able to access or change the data simultaneously, because that will affect the integrity of the data, especially in database systems. Probably if you've taken ComSci 127 and you've talked about transactions, and of course in transactions, transaction management, we have locks, for example, to be able to impose or implement the correct access to data. So this is what we mean by clustered system. Okay, so I am familiar with the setup clustered system because I've worked on several setup for clustered system. I've assisted ComSci 180, and my study is on high performance. My research actually for PhD is high performance computing using clustered system. So I have a setup here in the lab for these types of experiments. And an interesting component, of course, is the storage area network, because in a clustered, I think the most relevant project for this is the Human Genome Project. The Human Genome Project was a project that to sequence the human genome, and of course that will generate a lot of data. So we have a big system here, storage area networks, and the processing done by independent computers. So that is what we mean by the clustered system. Okay, so let me check again the Slack channel. Have question. Okay, so I'll okay, nothing specific to the topic. So we proceed now to the next section. Okay, so for those of you who built your own machine, okay, this is an example illustration of a typical desktop PC motherboard. Okay, so we have different slots here. We have the PCI bus slot. You have the processor socket, the DRAM slots, and of course you have different ports for the different peripheral devices like HDMI, PS2 devices, mouse or keyboard, LAN port. Okay, we have here the LAN port. We have the USB, probably power USB. Then for multimedia connections, we have HDMI. So this is what you see when you open the casing of your machine. Okay, and this is where you place, let's say your i7 processor. If you buy your own, you build your own. This is where you place that. Okay. So this is a typical motherboard. Okay. So we now move on to the next section, which is operating system operations. And we now, in the previous sections, we focused on the hardware because, as I said, we need to have an understanding of the hardware before we can understand, before we go into the details of the operations of the operating. So, in most machines, we have what we call the bootstrap program or a bootloader, which is a simple code to initialize the system and load the operating system kernel. We have a lab for this. This is lab 3. Right? So when you buy a machine, a PC, for example, it has a software called BIOS or UEFI or UEFI. This acts like a firmware, and it looks for a bootstrap program on the specified boot devices, and then from there it loads that small piece of program, and that small piece of program called the bootstrap program is the one that transfer control to the kernel of the operating. Okay, so first at the top we have the BIOS, then loads the bootstrap program, and then the kernel loads, and then the system daemons start. Okay, so when you have a Linux box, this is what happens, and then you get now the user interface provided by the operating system. So this is the machine. So normally you see this, you see the daemons starting during the boot up process. The MESG is a command to display the kernel ring buffer that is used to process the things that is being done by the kernel, like the different drivers. But this is the typical setup, or the typical steps being taken by the operating system before the operating system is loaded. And it is important to note that the kernel is interrupt driven. Okay, so we discussed interrupts earlier, and the interrupts can either be a software interrupt like a trap or an exception, or a hardware fault. Okay, so it's an hardware interrupt or a fault. Okay, and when we talk about software interrupt, as I mentioned previously, we talked about exception and trap. Okay, hardware interrupts are again called faults because, for example, general page protection fault. Okay? That is something related to the paging system of the machine. So it's a hardware interrupt that is being triggered, but the operating system can catch that. Okay? Now, most interrupts handled by the operating system are software interrupts, either exception or a trap. And these interrupts are triggered, for example, either by a software error. So, for example, if you divide by 0, okay, and that will trigger an exception. Divide by 0 exception, and the operating system should be able to catch that. Or a user program executes a system call. A system call is a type of service that is somehow privileged, and only the operating system can do that. Because as we will see later, when we talk about multiprogramming and multitasking, okay, there are certain operations that only the operating system kernel is allowed to do, or privileged operations. And that is accomplished via system call. You can think of this as like ordering in McDonald's. If you order from McDonald's, you are the user program. Then if you're going to order from McDonald's, you're going to talk to the staff to get your order. But you are not allowed to go inside the production room of McDonald's. Once you get your order, okay, you get your burger, that's it. Okay, so by telling your order to the cashier or to the staff, you're actually invoking some kind of system call. You don't care about what's going on underneath, but as long as you get your burger, that's it. Okay? The same case when you go to Jollibee. You can think of Jollibee as an operating system, McDonald's as an operating system, KFC, by the way, is closed already, as an operating system. But you are the user, and they have different operations underneath and can only interact via the staff. So that's called a system call. Okay? And also, these interrupts or these traps or exception can be triggered when other processes or other problems happen. Like there's an infinite loop, okay, and invalid accesses. For example, one process trying to write or read something from another process, because operating systems provide usually some form of protection so that one process will not be able to access another process. Process address space. I mean, okay. So in this slide, the important thing to remember is that the operating system or the kernel is interrupt driven, and we have these three steps to that happens when before the actual operating system is loaded. Now, we also have a concept of multiprogramming. Okay, so remember that the computer has computing resources like the CPU and the I/O devices. And the problem is, even though if, you can observe this, if you have a high-end machine, let's say you have an i7 and you have 16 gig RAM, and you're only running, for example, Minesweeper, right? That's a lot of resources being not being utilized. So the operating system designer realized this, and they introduced multiprogramming. So the idea here is to get the more programs can be placed in the main memory, and some of these programs can be selected to execute. That is the idea of multiprogramming. It organizes the jobs or the programs, code, and data so that the CPU has always one to execute. For example, I wrote a program that reads to a file, that reads from a file. Okay? While waiting for the result of the read, other programs can use the CPU. So in this way, the CPU is not sitting idle while my program is waiting for the completion of the read. That's the idea of multiprogramming. And the selection of which job to execute is done by a scheduler. So there is a concept now of job scheduling. Okay? So imagine this system. So this is my Linux box, and there are a lot of programs running. So this is called multiprogramming. Imagine when I run top in this system, I only have one line in this output. So that means there are a lot of wasted time. The CPU is doing nothing. So the idea for multiprogramming, okay, put in more tasks, okay, so that the CPU will always be busy. Especially this is a 32-core machine. So you can see that a lot of processors here are idle, meaning they are not doing anything. Okay? So imagine I only have one line here. then that will be a waste of resources. So when a job has to wait for I/O completion, right, it switches to another job. That's multiprogramming, or batching actually. Now, an improvement to multiprogramming is called multitasking. Okay. Before I proceed, I'm going to continue the lecture until the end of the section. But you can, if you're watching live, you can actually leave 10 minutes before the time. But my goal is always to finish the target section during this lecture. So I can extend this, but you are not required to watch until the end. You can leave 11:50 or 12 o'clock if you want. Okay? So multitasking is related to as an improvement to multiprogramming. It's very similar, but the purpose here is interactive computing. Okay? In the previous one, multiprogramming, this is actually batch system. This is used in the old days when there are mainframes. Nowadays, multiprogramming is no longer somehow practical because we have high-end systems, and with what we can do is multitasking. And the idea here is the CPU, the switching of the CPU from one job to another is so fast that the user does not notice that. Okay? And we need to have a response time that should be less than 1 second. Most modern operating systems are multitasking operating systems. These processes here, they move from one, they are scheduled so fast that you never notice that the CPU, which process is running, because the switching happens so fast. And each user has at least one program executing in memory. So it's called a process. So this is when the process abstraction was developed. This means that the processes are running programs. We'll discuss this. We have allowed for this, but this is where the process abstraction was developed. And if several jobs are ready to run at the same time, we have CPU scheduling. So take note that these are the things, actually these are the subtopics that we are going to discuss in the later meetings. Okay? So process abstraction, CPU scheduling. Okay? Now, there are also things like swapping. The idea of swapping is, remember that in the von Neumann architecture, the programs or the instructions should be in the main memory before the CPU can execute them. But there are instances wherein the program is so large that they cannot fit in one space allocated to it by the operating system. So some parts will be left to the secondary storage. And the idea of swapping is to be able to provide somehow a mechanism that even though some parts of the program is not in memory, it can still execute. Because unlike in the multiprogramming system, everything related to the program should be in the main memory. But here, in the swapping, multitasking, even though some parts of the program are not in the main memory, the program can still execute. And we'll have some discussion about this later. And then the last one is virtual memory. So virtual memory is related to swapping. The idea of when we talk about operating systems, we're going to talk about two types of memory. We have the physical memory, and we have the virtual memory. Okay. Physical memory is the actual memory provided by the hardware. For example, in my machine, So this server machine has 94 gigabyte of RAM. So that is a very big amount of RAM. Okay? So I don't know if any process can utilize that entire RAM, but in some applications like bioinformatics applications, Sir Aryan is actually running some of his bioinformatics applications on this machine because those applications require lots of memory. Okay? So they introduced the concept of virtual memory such that processes can only see the virtual memory and the operating system is the one that manages the physical memory. And that is essential. These concepts, swapping, virtual memory, are essential in multitasking. Okay? So that's basically it. So, and here is a memory layout of a multi-program system. So we have, this is the address. So the lowest memory address is 0, and then you have the maximum memory. So let's say this is 94 GB as I have in my server machine. Then normally the operating system is loaded in the high memory area, called the high mem. So when the boot sector or when the bootstrap program loads the kernel, it will load that in a specific memory at the top memory area, in the high memory area. Then the different processes will be allocated or will be placed in different memory areas also. Later on, I will show you how to view the location of the processes in the main memory. But this is what we mean by multiprogram. So without multiprogramming, only one process is running. These are empty slots. But with multiprogramming, as long as there is space in the main memory, we can place a process there. This way, we are able to utilize the memory resource efficiently. And the next one is, okay, so that's the memory layout. The next one is the dual mode operation. Again, these are general concepts on how the operating system operates. Meaning, while it is running now, what's happening? What are the main concepts behind it? Okay? The next item, so in the previous discussion, we talked about multiprogramming and multitasking. This one, we talk about dual mode operation because operating system actually are operating in dual mode. And usually these are called the user mode and the kernel mode. Okay? The dual mode operation allows the OS to protect itself and other system components. Okay? Imagine that you have a multi-program system and you don't have dual mode operation. This program can actually modify the operating system. Okay? During the early days in my undergrad years, we only have the disk operating system. A very simple operating system, and I can actually write a program to change the code in the operating system. And during the early days, I used to study writing computer viruses. Okay? So I write a program and find the location of a particular data structure or function in the operating system, modify that, and make my program infect other programs. So without this protection, like DOS did, then there is a problem when it comes to other processes messing up other processes, right? So there are two main modes. We have user mode and kernel mode, and there is a hardware component called the mode bit. The mode bit is a flag. It's actually a flag in a specific register in the case of x86 that distinguish it whether the operation to be performed on that particular memory area or memory access is protected or not. Okay, so it's the mode bit that provides the ability to distinguish when a system is running user code or kernel code. Okay? And when a user is running in when a user code is running, it's the bit is user, and if the process running is in kernel, it's called the mode bit is kernel. So how do we guarantee that user does not explicitly set the mode bit to kernel? Okay, so it is the system call. Okay, the system call is the one that actually changes the mode to kernel, and then it resets it back to user mode later. Recall the analogy when ordering your burger from McDonald's. So the system call, we can think of the system call as the staff, okay? And that staff, okay, it needs to perform, let's say, making the burger, okay? So it's the system call that does this, that changes the mode from kernel to user or user to kernel. And this is so because some instructions are designed to be privileged and only executable in the kernel mode. So that is the dual mode operation. So always remember that when you are using an operating system right now, while you are looking at your computer, the operating system operates in user mode, kernel mode. So it switches, whenever you do an action on your operating system, it switches from user mode to kernel mode. Okay? So this is a better illustration of that. So let's say you have a user process. So let's say you have the hello.c. I will not write the code, but you know the hello.c example, which simply prints printf hello world. That is your user process. Okay. So while the user process is executing, somewhere in your code you have the printf code, the printf function is part of libc. Okay, and what happens is printf needs to write something to the screen, right? Because you want to display hello world. Now that printf will actually invoke a write system call. This one is a user function. This one is a syscall function. So this one can be executed by the kernel only. Okay, it will switch when this write is executed. The operating system will switch from user mode to kernel mode, and this is the trap, which is the syscall. Then execute write, which will display something on the screen, and then go back. Okay. Why is this important? Why is the write system call should operate in the kernel mode? Okay? Because it is a protected operation. Okay? You don't want any process to be writing anything on the screen. For example, if a user process, if this is not a privileged instruction, a user process might mess the display of other processes. That's why it should be run in kernel mode. Okay. Usually you have a display driver that controls that. So the kernel will talk to the device driver. Okay, write this on the screen at these coordinates given this text attribute. Okay. So that's what we mean by that. So whenever you always remember in COMSI 125, after taking COMSI 125, you should always remember that whenever you interact with your operating system, you do anything with the operating system, always remember that there is a transition from a user mode to kernel mode from time to time. It's not just I have access to everything. There's always a transition from user mode to kernel mode. Okay. So I think so I hope that covers the idea of the transition from user mode to kernel mode. So the last one for these operations is the timer. Okay? The timer is very important. Okay? In a multi-programming system like this, I said a while ago that you only have one CPU here. Let's say we have the CPU. You only have one CPU, one core, and you have 4 processes, 1, 2, 3, 4. Only one process can run in the CPU at one time. Okay? So what if process 4 went into an infinite loop? If process 4 went into an infinite loop, then it will hug the CPU. No other processes will be able to execute on the CPU because process 4, there is an infinite loop, so it's always executing on the CPU. How can the operating system gain control? Okay? And that is the importance of the timer. Okay? So that whenever a process misbehaves, the operating system can always take control of the machine, of the operation. So the timer is used to prevent infinite loops or process hogging resources. Okay? So let's say the idea here is, let's say, all right, process 4 has an infinite loop, but when we have a timer, if this process 4 is already running, let's say, too long, automatically the control will be transferred to the operating system. That's the essence of the timer. Okay? So the timer is set to interrupt the computer after some time period. Okay? So that the operating system will take control of the execution. Okay? So you keep a counter that is decremented by the physical clock, and then the operating system set the counter. So it is a design decision. Okay, how long? Okay, to set the counter, and then when the counter becomes 0, it generates an interrupt and control is transferred to the operating system. Okay? The control, so the operating system will take back. That means that in our drawing, okay, process 4 is in infinite loop, but after some time, OS will be running on this. Okay? And if you press Control C, for example, okay, so this is an infinite loop. You press Control C, okay, that will be received by the process, okay, and then can execute. So even though you have an infinite loop, not Control C, it's Control Z, for example. You press Control Z, okay, so the OS will take control. Okay. So usually, this is set up before the scheduling process to begin to regain control or terminate the program that exceeds the allotted time. Okay, so I guess this covers the objective for this lecture. And again, if the question comes to your mind, how can the operating system seems to always have control? This is because of the timer. And the importance, of course, the important thing to remember is the interrupt, the hardware interrupt. A very high priority interrupt, meaning if this interrupt is triggered, the timer interrupt is triggered, you can't ignore it. Okay? There are some interrupts that you can actually disable. Okay? In the x86, we have the CLI, which is clear interrupt, meaning when a program is running, it will not be interrupted. Okay? But the timer interrupt is hardware interrupt that cannot be ignored. You have to handle. You are forced to. The CPU is forced to uh, address this or to process this timer interrupt because of this purpose. Okay, so we'll end here, and I will consider some of your recommendations regarding the streaming for next week's meeting. And the other videos again will just be recorded like in the other one, and we will meet again on Friday next week. Okay, so enjoy your lunch. Thank you very much for